This presentation is one of 6 on non-destructive testing. The topics covered by the other presentations are Introduction to Non-Destructive Testing, Penetrant Testing, Magnetic Particle Testing, Radiographic Testing, and Eddy Current Testing. This presentation is an introduction to ultrasonic testing. The material is not intended to train individuals to perform NDT functions, but rather to acquaint them with the NDT equipment and methods that they are likely to encounter. Knowledge of the basic principles and typical applications should enable them to know when to call for help from experts. The ultrasonic testing method uses high-frequency sound to perform inspections or measurements. The frequencies typically range from 500 kHz to 20 MHz. The method may be applied to a wide variety of material forms, such as castings, forgings, welds, and composites. The method is suitable for detecting discontinuities, measuring thicknesses, and correlating the velocity of sound to physical properties of the material. We will start with the basic principles of sound, followed by a discussion about how transducers generate and detect ultrasound. Next, we will cover the principles of ultrasonic inspection, including test techniques such as pulse echo through transmission, normal beam, angle beam, contact, and immersion. A couple specific inspection applications will illustrate how the methods are applied. Some detail will be provided about ultrasonic inspection equipment and methods of data presentation. Finally, we will summarize the advantages and limitations of ultrasonic testing and define some of the specialized terms used. Sound is a traveling wave of vibrations in a material. The material can be a gas, liquid, or solid. The individual particles of the material vibrate to transmit the sound. The pitch of the sound is the frequency of vibration, number of cycles per unit time. The human ear can hear frequencies up to about 20 kHz, 20,000 cycles per second. Ultrasound frequencies are so high that they cannot be detected by the human ear. The typical frequency range for ultrasonic inspection is 500 kHz to 20 MHz. Some ultrasound leak detection methods go as low as 40 kHz, and acoustic microscopes go as high as 2 GHz. Sound waves travel in a material. Imagine for a moment that the sound wave is frozen in time. The distance between 2 points of the same phase on the wave is the wavelength of the sound in the material. For example, the distance may be measured from crest to crest or from trough to trough. The time it takes a sound wave to travel a distance of 1 complete wavelength is the same amount of time it takes the source to execute 1 complete vibration. The velocity of sound in a material is a property of the elastic constants of the material. Thus, the velocity of sound is a constant for a given wave mode and material. In fact, the velocity of sound is the constant of proportionality between the wavelength and frequency of the sound. The wavelength is inversely proportional to the frequency. That is, high frequencies have short wavelengths and low frequencies have long wavelengths. One way to remember the relationship between velocity, wavelength, and frequency is to remember the dimensional units. Velocity has units of length over time, wavelength has units of length, and frequency has units of inverse time. There are many different types of wave motion possible. The particle motion is in the same direction as the wave for longitudinal or compression waves. The particle motion is perpendicular to the wave direction for shear or transverse waves. The particle motion is in the shape of an ellipse on the surface of a solid for Rayleigh or surface waves. Each of these wave modes has a different dependence on the elastic constants of the material, and thus they each have unique and different wave velocities. Gases and liquids cannot support shear in the material, and thus longitudinal waves are the only type of wave mode in these materials. Ultrasonic waves can be reflected, refracted, and focused. Reflection occurs when the sound wave interacts with a material with a different acoustic impedance. Acoustic impedance is the product of the velocity of sound and the density of the material. Thus, reflection can occur between 2 materials with the same velocity of sound if the density is different. Usually, both the density and velocity of sound is different between the 2 materials. No reflection would occur between 2 different materials if their acoustic impedances are equal. The amplitude of the sound reflected from and transmitted across an interface can be calculated from the acoustic impedances of the 2 materials. Generally, the sound tends to stay in the material with higher acoustic impedance. No refraction or change in direction occurs if the incident sound is normal or perpendicular to the interface between materials. If the incident sound is not normal to the interface, the sound will refract or change direction. The change in direction can be calculated, knowing the velocity of sound in the two materials. For non-normal incidents, additional wave modes may also be generated in order to satisfy the boundary conditions at the interface. Thus, for example, a longitudinal sound wave in water, incident at an angle other than 90 degrees to a steel surface, will generate a refracted longitudinal and shear wave. If the incident angle is increased enough, a surface wave can also be generated. Discontinuities in solids such as cracks, inclusions, and porosity are relatively low in acoustic impedance and thus reflect sound, thus allowing their detection. Sound is generated and detected using transducers. They are called transducers because they transform electrical energy into mechanical vibrations or vice versa. An internal piezoelectric element has the property of changing thickness when a voltage or charge is applied. A typical transducer has a piezoelectric element with a conductive electrode on opposite faces. The outside face is grounded and the voltage is applied to the inside face. A backing material is used to dampen the vibrations and tune the response to a specific range of frequencies. The outside face may be protected with a wear plate for manual contact inspection, or be fitted with a wedge to generate a refracted, mode-converted wave, or with a shaped face to focus sound for immersion testing. Now that we have discussed the basics of sound generation, let's discuss how ultrasound may be used for inspection. The transducer generates a pulse of ultrasound. The wave pulse travels in a straight line and at constant velocity until it encounters an interface. At the interface, some of the energy is reflected and some is transmitted across the interface, depending upon the acoustic impedances. If the interface is due to a discontinuity or internal defect, the reflected or transmitted energy can be detected and provides information about the location and size of the reflector. The location of the reflector can be deduced from the round-trip travel time for the pulse because the velocity is known. The size of the reflector can be deduced by scanning the transducer and comparing the amplitude of the signal to known reflector sizes at the known distance. The choice of inspection technique depends upon a number of factors, including the geometry and material of the test article and the type of feature to be detected. There are three primary classifications of test techniques. Pulse echo and through transmission techniques relate to whether reflected or transmitted energy is used. Normal beam or angle beam relate to the direction of the sound as it enters the test article. Contact and immersion relate to whether the transducer is coupled to the test article using a thin layer of couplant or immersed in a liquid. Let's discuss these techniques in a little more detail. In the pulse echo technique, a transducer sends out a pulse of energy, and the same or a second transducer detects the reflected energy or echo. A series of pulses are generated and the amplitudes of the received echo signals are displayed on an oscilloscope type display. This type of display is referred to as an A scan. The pulse repetition rate can usually be set fairly high, a few thousand pulses per second, because the velocity of sound in liquids and solids is relatively fast. The pulse repetition rate limit is set by the round-trip travel time for all the internal echoes. The next pulse should not be sent out if it would interfere with echoes which are still occurring. Otherwise, interpretation of the A scan becomes difficult. The example illustrates the initial pulse, a crack echo, and back surface echo. The times the echoes appear depend upon the round-trip distances. The amplitude of the echo depends upon the distance the sound has traveled and the size and orientation of the reflector. If the crack reflector is large enough, the back surface echo may completely disappear. This slide shows an actual example of pulse echo inspection using a contact transducer and side drilled hole placed midway in a steel block. The first A scan shows only the front surface or initial echo and the back wall echo. The second A scan shows the presence of the hole midway between the front and back echoes. Note also that the back surface echo is also reduced in amplitude. The pulse echo technique allows testing when access to only one side of the material is possible. The instrument also has been set up with the correct material velocity, such that the time axis may be interpreted as depth of reflector. Sometimes the through transmission technique is the best method. In this case, transducers are located on opposite sides of the test article. One transducer generates the sound and the other transducer detects the sound. Discontinuities in the sound path decrease the received signal amplitude. Since there is no time information about the discontinuity, which reduced the signal strength, there is no information about the depth of the discontinuity. This technique is good for materials which attenuate the sound so much that the round-trip signal is too small to detect. This slide shows an actual example of through transmission inspection using two contact transducers and side drilled hole placed midway in a steel block. The first A scan shows a strong received signal. The second A scan shows a reduced received signal due to the presence of the side drilled hole. The time the received signal arrives can be used to measure the thickness of the steel. This slide discusses the normal and angle beam classification of inspection techniques. A wedge of material with acoustic impedance less than that of the test article is usually used to refract the sound beam at the desired angle. This method is used to direct the sound normal to the reflector of interest in order to produce the largest signal possible, or if surface features interfere with normal beam inspection. In some cases, the refracted beam may make several internal reflections in the test article before reaching the region of interest. Air has a very low acoustic impedance. Both the density and the velocity of sound are low for gases when compared to solids. This means that the sound generated inside the transducer will tend to stay inside the transducer. In order to get the sound into the test article, the sound generated by the transducer must be coupled to the test article using an intermediate material whose acoustic impedance permits the sound transmission. Usually a liquid is used to match the impedances of transducer and test article. For contact testing, the liquid couplant could be water, oil, or a gel. For immersion testing, the test article is placed in a liquid bath. The liquid is usually water, although other liquids could be used. In immersion testing, the bath allows better coupling and easier movement of the transducer. The A scan for immersion testing shows an additional signal from the front surface, which occurs at the round-trip travel time of the echo in the liquid. Otherwise, the signal interpretation is the same as that of contact inspection. Now that we have discussed the classifications of inspection, let's discuss some inspection applications. One application is flaw detection for defects such as cracks, inclusions, porosity, etc. Another application is thickness gauging, either as a measurement method or to detect erosion or corrosion damage. Through transmission signal amplitude can provide an estimation of void content in composites and plastics. High-frequency refracted backscatter can provide a measurement of case hardening depth in steels. The grain size of metals may be estimated. Measurement of various wave mode velocities may be used to compute the elastic constants of materials. Many other problems can be solved, depending upon the feature of interest and an understanding of how the basic principles may be applied. This slide illustrates one type of thickness gauging. Petrochemical industries routinely use this technique to measure erosion or corrosion damage. Specialized inspection instruments sometimes simply report the measured thickness. The battery-powered portable instrument shown includes both an A-scan and the resulting digital thickness measurement. The A-scan presentation is often useful to understand the nature of the reflections and to ensure that the correct thickness is reported. The thickness range which can be measured can vary from tens of inches to a few thousandths of an inch. Generally, the thinner thicknesses are more difficult to measure because the echo arrives while the initial pulse is still decaying. Special transducers are used with special calibration techniques to provide accurate measurements for thin wall measurements. This slide illustrates one particular flaw detection application. Rolled steel beams can develop internal delaminations. The upper A-scan shows multiple internal reflections in an unflawed region of the beam due to the thickness of the steel. The lower A scan shows multiple internal reflections with a much closer spacing due to a delamination close to the front surface. The delamination is so large that no part of the sound makes it to the back surface at all. Angle beam inspection is often used for flaw detection in weldments. The top bead of the weld is often too rough for normal beam contact inspection. The refracted beam can be aimed approximately normal to the heat-affected zone of the weldment, which often contains cracks. Applying this technique requires considerable skill, as the transducer must be oscillated towards and away from the weld while simultaneously understanding that the sound path length changes. The transducer also needs to be translated parallel to the weld. The equipment used to perform the inspection can have a large impact on the results. We will discuss the choices of transducers, instrumentation, and calibration standards. There are thousands of choices in transducers. They vary in size, shape, and function. Generally, however, they may be classified as either contact or immersion, single or dual element, and normal or angle beam. It is often important to select a specific frequency range or bandwidth, size, and focusing for specific applications. Contact transducers are usually designed to be easy to hold and to withstand wear during rigorous use. Dual element transducers contain both a transmitter and receiver in a single housing. This type of transducer is sometimes referred to as a pitch-catch transducer. One advantage to this configuration is that the receiving transducer is always ready to detect sound and does not have to recover from transmission of a pulse. This type of transducer is often used to measure thickness in thin materials. The two elements also often have a small roof angle at the top of a delay line, such that the two refracted beams intersect at a specific distance beneath the surface. Delay lines can also be used with single element transducers to improve near surface resolution. The delay line acts somewhat like the water path for immersion transducers, in that it provides a time delay between the sound generation and reception of reflected energy. If the transducer is designed with interchangeable front pieces, replaceable wear caps or flexible membranes may be used. In all cases, a couplant is placed between the transducer and the front pieces. In this case of a flexible membrane, a fairly thick layer of couplant may be used to help conform to curved or rough surfaces. A material with low thermal conductivity may be used as a front piece for high temperature measurements. A wedge may be used to refract sound at the interface for contact transducers. The angle of refraction is given by Snell's law, which states that the ratio of the sine of the incident angle to the velocity of sound in the wedge is equal to the ratio of the sine of the refracted angle to the velocity of sound in the test article. If the incident wave is longitudinal, both a refracted longitudinal and a refracted shear wave can be generated. The velocity of sound for a shear wave is less than the velocity of sound for a longitudinal wave. This means that the shear wave will refract through a smaller angle than the longitudinal wave. There's a critical incident angle beyond which the longitudinal wave has been refracted to 90 degrees. Similarly, there is a critical incident angle beyond which the refracted shear wave will reach 90 degrees. In this case, a surface wave is generated. The wedges are often designed with an adsorbing layer, ridges, or special curved shape to keep internal reflections in the wedge from interfering with signal interpretation. Immersion transducers use a liquid to couple the sound from the transducer to the test article. Lenses may be applied to the active element to direct or shape the exiting sound, much like the wedge on contact transducers. A flat lens simply produces a planar wave. A cylindrical lens produces a beam which is focused to a line at some focal distance from the transducer. A spherical lens produces a beam which is focused to a point at the focal distance. This focusing of the sound beam improves the sensitivity of the transducer to small defects. If a spherical focused transducer is placed closer to the test article than the focal distance of the sound beam in water, the sound will be further refracted when entering the test article. This effective focal depth in the test article can be calculated and used to maximize sensitivity at a specific depth. There's a wide range of ultrasonic inspection instrumentation from special purpose to general purpose. Instrumentation may be portable or stationary, contact or immersion, manual or automated. The equipment may be for thickness measurement, sometimes called D meters, flaw detection, industrial, or special application. Special purpose thickness gauges often use dedicated transducers and provide a digital readout. Many general purpose instruments also include a digital readout for the thickness measurement application. The simple gauges are often used for erosion or corrosion inspection. Flaw detector instruments are mainly used for inspection of components for defects. Older instrumentation used CRT oscilloscope type displays for the A-scan. Newer instrumentation is all digital. Time gates may be used to select a specific echo for interpretation. Similarly, the amplitude may also be gated to measure the echo amplitude or to provide an alarm signal. If the ultrasonic instrumentation is placed in a production environment, the instrument will typically include many automated features and not be portable. In immersion testing, if the transducer is scanned and the amplitude of a time-gated signal is plotted versus the transducer location, a C-scan image of the test article is generated. Here's an example of some C-scan images. The left image uses the echo from the front surface. The right image uses the echo from the back surface. The reason for the varying amplitude is that the surface acts like a mirror and reflects varying amounts of sound depending upon the angle of incidence. The image from the back surface still shows features from the front surface because the sound that makes it to the back surface must first be transmitted across the front surface. Since different materials have different acoustic properties, a method is needed to calibrate ultrasonic test equipment for proper interpretation of the received signals. This is accomplished using calibration standards. The standards come in many different materials and configurations depending upon the application. A key factor in ultrasonic inspection is the velocity of sound. Thus, calibration standards are typically manufactured of the same material as that of the test article. Thickness calibration standards may be curved or flat, depending upon whether they are used for plates or tubes. These standards typically take the form of step wedges of varying known thicknesses. The echo amplitude of a given size flaw will decrease with distance from the transducer. Thus, if echo amplitude is being used to estimate the flaw size, calibration standards are needed with the flaw size and known depth in the material. Distance area amplitude standards are used to create a distance area curve on the A-scan for proper interpretation. If the plane of a flaw is not parallel to the entry surface, angle beam inspection is used to maximize the received signal. In this case, calibration standards are needed to calibrate the response for angle beam transducers. This slide illustrates a number of different standards, each designed for a specific geometry or application. There are many codes regulating the use of ultrasonic inspection. These codes often specify the calibration standards and the methods to be used for inspection. This slide illustrates just a few of these standards. The data from ultrasonic inspection can be presented in many different forms. We have already mentioned two of these forms, but we'll discuss them in a little more detail. The A-scan displays the received signal amplitude versus time. The amplitude may be used to estimate flaw size by comparison to calibration standards. The time of arrival of the echo may be used to measure the distance or depth of the reflector. The top A-scan displays an unrectified or RF waveform. The bottom A-scan displays a rectified waveform. Sometimes the unrectified waveform is useful to determine the initial direction of phase change, which depends upon the change in acoustic impedance. We have not mentioned the B-scan before. If the transducer is scanned while the time-gated amplitude signal is plotted versus time, essentially a cross-section image is created. The C-scan is a plan view of the test article with either a monochrome or color-coded image. Each point in the image corresponds to either the amplitude or arrival time of the signal at the corresponding point on the test article. The transducer is held by a search tube whose X, Y, and Z coordinates may be automatically controlled. The longitude and latitude of the transducer may also be adjustable. Furthermore, the test article may be placed on a turntable. Thus, up to 6 degrees of freedom may be used to generate a scan which follows the geometry of the test article. Ultrasonic testing has many advantages for non-destructive testing. The method is sensitive to both surface and subsurface discontinuities. The depth of penetration for flaw detection or measurement is superior to other methods. Only single-sided access is needed when the pulse echo technique is used. Ultrasonic testing provides high accuracy in determining reflector position and estimating size and shape. Only minimal part preparation is required. Electronic equipment provides instantaneous results. Detailed images can be produced with automated systems. Ultrasonic testing has other uses, such as thickness measurements, in addition to flaw detection. Ultrasonic testing has several limitations. The surface must be accessible to transmit ultrasound. The skill and training required is more extensive than with some other methods. Ultrasonic testing requires a coupling medium to promote transfer of sound energy into test specimen. Materials that are rough, irregular in shape, very small, exceptionally thin, or not homogeneous are difficult to inspect. Cast iron and other coarse-grained materials are difficult to inspect due to low sound transmission and high signal noise. Linear defects oriented parallel to the sound beam may go undetected. Reference standards are required for both equipment and calibration and characterization of flaws. The following glossary of terms defines some of the terms used in ultrasonic testing. The acoustic properties of interest for ultrasonic testing refer to characteristics such as velocity, impedance, and attenuation. ASTM is an abbreviation for the American Society for Testing in Materials. This society is extensively involved in establishing standards for materials and the testing of materials. Back reflection is a displayed signal that corresponds to the far surface of a test specimen from the side opposite the transducer when testing with longitudinal waves. Bandwidth is a range of frequencies which may be narrow or broad. B-scan is a presentation technique displaying data in a cross-sectional view. Calibration is a sequence of instrument control adjustments and instrument responses using known values to verify the instrument operating characteristics. Calibration allows determination of unknown quantities from test materials. CRT, of course, is an abbreviation for cathode ray tube, which is a vacuum tube that utilizes one or more electron guns for generating an image. C-scan is a presentation technique that displays a specimen data in a plan-type view. DAC, or distance amplitude correction curves, is a graphical method of allowing for material attenuation. The percentage of DAC is often used as an acceptance criteria. A discontinuity is an interruption in the physical structure of a material. Examples include fissures, cracks, and porosity. IIW block is a calibration standard meeting the specifications of the International Institute of Welding. Longitudinal or compression wave is an ultrasonic mode of propagation in which the particle vibration is parallel to the direction of propagation. Near surface resolution is the ability of an ultrasonic system to display reflectors located close to the entry surface. Pulse echo is an ultrasonic test method that utilizes reflected sound as a means of collecting test data. Rayleigh or surface waves is an ultrasonic mode of propagation where the sound travels along the surface with elliptical particle vibration. Reflection is the changing in direction of sound waves as they strike a surface. Snell's law is an equation of ratios used to determine the incident or refracted angles of sound. Sweep display is a horizontal line on the lower portion of the display, often called the time baseline. Through transmission is a test technique in which ultrasound is transmitted from one transducer and received by a separate transducer on the opposite side of the test specimen. Wavelength is the distance that a sound wave travels as it completes one cycle, normally measured in inches or millimeters.